J'ai pas voulu, je le connaissais pas. Moi, je me rappelais pas. Avec ce formulaire, c'est quoi ma résultat? Est-ce que tu vas genre 5 quiz, tu vas compter les 4 meilleurs, je pense? Whatever your time allows. Okay. All right, guys. So it's been a while since I've done it. We're actually seeing each other once this week, which puts you guys now in the back end of like the 2 groups, and now you guys are the last group to get each lesson. That's actually good for you guys because that means that I'll have to practice it twice before showing it to you guys. So hopefully today's class is a better one. Last time there was a lot of confusion. Totally understandable. It's not an easy topic. We're going to go over 2 more examples that relate to last class so that we're sure to most of you understand it and then we can move on. There's one thing I made a mistake about last class. I want you guys to take your notes and go back to those problems that we're working on. It has to do with the volume of a sphere. We learned that it was rho dV if we wanted to get dq. This is what we wrote in your notes that we were working on in that last slide, or the before last slide, I can't remember. This is PowerPoint, by the way. And rho was some function, I think it was 1 minus 4r over 3r, like that. Is that it? You guys remember? Yeah, okay. And then we said the dV. The dV is where I made a mistake. In order to find the volume of the sphere, you have to add a lot of hollow spherical shells together, kind of like an onion. And each hollow spherical shell has a surface area of 4 pi r squared. Right? Each shell has a surface area of 4 pi r squared and a thickness dr. Okay? The mistake I had made with you guys was that I divided this by 3, which I shouldn't have done. Okay? So make sure that that's clear in your notes, because it comes up again when you're working on the problems at home. That comes up again, and I don't want you guys thinking that there's a mistake with the answer. It was actually a mistake last week with my notes. Okay? So there is no divided by 3 here. All right. So I came up with 2 questions to get you guys back into the mode a little bit, and then we'll change gears a little bit. Today's lesson is not as hard as the last 2 have been, but it's still kind of different enough that you'll need to be paying close attention. So let's start with this problem. Determine the charge of that cylindrical object. All right. That cylindrical object has some radius r, has a length x, and has a charge density indicated there. Now I'm going to ask you guys a couple questions. Based on what you see in this question, is this a uniform charge density or a non-uniform charge density? Before that, I am. It's okay. The room is NYB02. Okay, it's going to be that for the rest of the semester. Okay, NYB02. So, this is 07, but I haven't. It's not going to be on the one there because I only added it today. K9.adobeconnect.com/NYB02. 02. So I'll repeat my question. Is this a uniformly charged cylindrical object or is it non-uniformly charged? How did you know that? Exactly. So I wrote that my charge density here is some constant multiplied by a variable to the power of 3. And that variable, is it referring to my radius or is it referring to my length? The length, right? And that's different. And that means that if I had this cylinder, right? If I had this cylinder, that means that the charge changes as you go along the cylinder. If it was a function of r, however, if my charge density was a function of r, what that would mean is if I had a cylinder, then it would change as a function of the radial distance outward from the center of the cylinder. Okay? So it depends on which variable I put in that charge density expression. It's going to tell you where the charge density is distributed. So in the first example, on the top one, I wrote that it's distributed along its length. And the second one, it's distributed along its radius. Yes? I can't because I need another room to do the problem. Do you want to connect to Adobe Connect so that way you can see it? It's NYB02. It's going to be NYB02 for the rest of the semester. You can just bookmark it, so that way you can go to it anytime you want. All right, okay, so we know that it's non-uniformly charged. We know that it's dependent on its length. I have another question for you. Is this rod, this cylindrical rod, is it going to be a thin rod or a thick rod? Thick? So what's the thickness? What's the radius of the wire? 10 to the minus 3 meters, which is 1 millimeter. So the thickness of this rod is actually really thin. And what about the length of this rod? Very long. So what am I referring to? A wire, exactly. All right. So I have a thin, long wire. It's 4 kilometers or something, 3.4 kilometers long. It's pretty long for a wire. Not necessarily realistic because if you're going to have a really long wire like that, you're going to be slightly thicker. But essentially, the idea is that we're trying to find the charge of an entire wire. We're not going to expect something really small as an answer as a charge. The charge on a 3 kilometer long wire should be something that's quite big. Okay? So now, the question always, whenever we're dealing with doing something like this, the question should always start the same. We should always find a small dq. And what's that relationship? dq is equal to what? You have to try to recall this from last class. It's not necessarily fresh in your brain. Are we dealing with a length? Are we dealing with a surface area, or are we dealing with a volume? Volume, okay. So there's going to be an expression of volume in there. What's the variable for charge density for volume? Rho, exactly. So I have dq is equal to rho, and then what else is next to it? Delta volume, but here I have small dq, so I'm going to have small d volume. Okay? That's how I'm going to start this. All right. So now it's a bit more tricky. So let's fill in what we know. dq, we're going to integrate that later. It's going to become q. That's no problem. Rho is 3.06 times 10 to the negative 6 x to the 3 times dv. Now that dv is what's tricky. So how can we break this cylinder down into really small lengths? What would it look like? Yeah, exactly. Like if you were to take
like a salami roll, and you were to slice it up into real small slices, that's what you would separate this because you're separating it lengthwise. So then we have to find the volume of each one of those small discs. How do you find the volume of a small disc? What's that? Yeah. PR squared H, or PR squared, but this time the thickness of this small, infinitely small, thick disk is going to be, what's going to be the thickness of that? Vx, exactly. All right. Now, if I want to find the charge of that small area, I can do that. But if I want to find the charge of the entire thing, I need to add them all up. So I'll integrate the left and I'll integrate the right. So if I integrate dq, I just get q, which is what I'm looking for, the entire charge of this object. And that's going to be the integral. And what are going to be my limits of the integral? And where do I start and where do I end? Exactly, from 0 to 3.4 kilometers. At this point, you've done everything you need to do to set up the integral. And for the purposes of the quiz that's next class, you guys got my email about that, right? So for the quiz next class, I just need you to stop here, okay? This will get you full marks. For the test, I'll ask you guys to solve the integral, but for the quiz, we'll stop here. Now, how do we solve this? Yeah, there it is. Yeah, definitely. There's a lot of constants. So 3.06 times 10 to the minus 6 is definitely a constant. What else is a constant? 5? Where? R squared, yeah. Yeah, you take R squared out. Everything else is no longer a constant, so I can now put back my integral. And that's not a very complicated integral. Is equal to 3.06. You guys can do this on your own now. I'm going to work it out on the board, but I want you guys to solve this on in your notebooks. You have an answer? Yeah, because you gotta put that in x, right? 3.4 times 10 to the 3 divided by 4. You didn't do this to the power of 4. It should be something like 3,000, I think. Is that what you got? 3,000. 3021. What units? Coulomb, very good. Yep. Yeah, I don't mind. One second. What's that? Oh, 321. Okay. Yep. Ceci, est-ce qu'on va prendre un tranche du saucisse, on va dire, puis la tranche va avoir une surface de cuillère carrée, fois l'épaisseur, DF. Je ne l'ai pas marqué là, mais l'épaisseur, c'est DF. C'est comme ça qu'on trouve le volume d'un petit tranche. Are you guys feeling okay with this? It's not so bad, right? You really want an apple, eh? Yeah. Okay. So, a lot of you are worried because I sent you this document that has 3 pages of integrals on it, and I'm asking you to know how to do integration. Well, you guys have passed Cal 2. I spoke to the Cal 2 teacher, and that's the document that you guys had apparently. And I'm comfortable with giving you guys that for you to work with on your problems at home and whatnot. In tests and exams, I mean, at the end of the day, we still are a physics class. Yes, you need to have learned your integrals. Yes, I'll expect you to learn the integrals, but I'm not going to ask you to learn and memorize those obscure identities or anything like that. Learn how to do integration by parts, learn how to do integrations by substitution, do the polynomials and some of the basic natural log identities. Those ones are the ones that you need to know. Okay, I don't think you need to know more than like 10 of those integral identities. But again, it's whatever is asked of you in Cal 2, you're going to be responsible for it here. Okay? Yeah. For this first test, you can, but after that, no. But again, I'm not going to, the problem is not, the purpose is not to test you guys on integration. The purpose is to test you guys on physics. So I'm not going to make it hard, promise. Yeah. Okay. Any questions about this? All right, let's move on to a second question. This one is more simple, but it requires more steps, if that makes any sense. It's a, this one actually didn't work. We'll do it anyway, doesn't matter. We'll find an answer and I'll explain to you why it doesn't work at the end, and you guys could tell me how I could have fixed that. So there's a proton being launched at 4 degrees above the horizontal. That's what that means, okay? 4 degrees above the horizontal means this is the horizontal, and 4 degrees above it is where the proton is getting launched. The proton is getting launched at an initial velocity of 80,000 meters per second, okay? And I'm asking you, what is going to be the delta y of this proton after it passes through this, these parallel plates? Okay? This is essentially a projectile motion problem. I want you guys to change one thing for me though, okay? If you guys don't mind. Can we make the bottom negative and the top positive? So I'm going to cross this all out here. I'm going to put negatives at the bottom, positives at the top. And so therefore the top is going to be positive 40 volts, and let's make the bottom negative 80 volts. Okay? We'll leave the numbers there, we'll just change them So the top is 40 volts, the bottom is negative 80 volts. The length of these parallel plates is 8 centimeters. It's separated by a 4 centimeter space. Okay. And I want you guys to tell me what is the motion of this object going to look like? Yeah, exactly. So then, and then Newton said it was projectile motion. So it kind of looked like that. Okay. How did you guys know it was going, falling and going downwards? How did you not know that it was going to go upwards? It's attracted by the negative at the bottom. All right, so the bottom is negative, so it's attracted by the negative. If I had to draw field lines, yes, yeah? It's just positive 40 on the top now and negative 80 at the bottom now, okay? But ultimately, it doesn't make a difference because it's the difference that we're going to take, okay? Where do the field lines go? What do the field lines look like here? Yeah, top to bottom, exactly. So it's going to get messy now. But if you have to draw field lines, you would draw them from the positive to the negative, which is in this case top to bottom. And these are the electric fields that a positive charge will feel. If I were launching an electron, it would do the opposite. It would get attracted to the top. And it would look like, if it was an electron, it would look like that, or it would look like that. That kind of thing, like that. Okay? I'm going to erase that because it's useless. If it were an electron, it would get attracted by the top. It would just be an upside down projectile motion. And you guys can do that too. If I'm trying to find delta y in a projectile motion problem, which variables do I need to solve for? Which variables are important in projectile motion? See that? The speed of y, so I might need that at one point. So vy. What else? Acceleration, super important. Time, g, well, g is acceleration. So you said that one. Time, absolutely. And the one the question is asking for, yeah, distance, delta d, delta dx, or delta dy. We don't know yet, but those are these are the important things that we're going to need to know. All right. We definitely are going to need acceleration. So let's solve for that one first. Why is it so loud? It feels like you're all in here. Oh, there's a door there. Automatically, when you're talking about physics and acceleration, first thing you should think of is mass times acceleration. There's where you're going to get your acceleration from. What's causing this acceleration? Which force is causing this acceleration? Which one? Electrostatic force, exactly. So if it's electrostatic force that's causing acceleration, then I could write my expression for electrostatic force right there. But we have two expressions for electrostatic force. One that depends on the two charges, but then there's the one for the parallel plates that we talked about from last class. You guys remember what it was? What's it? QE, yes, absolutely. Okay. Do we have the electric field? We don't have the electric field, but we have an expression for the electric field. Do you guys remember what it was? It had to do with V, exactly, V divided by R, or delta V over R. So now I can solve for A. A is equal to Q delta V over M times R. And just fill in everything. The charge of a proton, you guys know what that is. The mass of a proton is 1.67 times 10 to the negative 27 kilograms. I'll write that here. You guys do the math. Tell me when you have an answer. The R in this case, what does that represent? Is what? 0.04 meters? Yeah, exactly. It's the separation of the plates. The delta V in this case, I wrote down that there's 120 volts. Okay, you guys know how I got that? That's the difference between what? 40 and minus 80. So it's not, sorry, 100, yeah, 120 volts. Sorry, I keep going your way. Can someone come up with an answer for me? Yeah, you have one? 2.87 times 10 to the 11? What are the units? Yeah, perfect. Is that an okay answer? I don't have a calculator, so I can't confirm. Yeah, you got that? You guys got that? Okay, good. All right, step one, check. We got our acceleration. All right, what's the second step? What do we need? If we're ultimately going to find delta y, what do we need? The time, yes, absolutely. Step two, let's find time. How do we find time? Yeah. Yeah. Yes, absolutely. So the horizontal distance is given to you. It's 8 centimeters. The velocity is given to you because of the angle and the velocity. And there is no acceleration, so you can find that out super easy. So vi cos theta is equal to delta dx over delta t, right? So that means that 80,000 cosine of 4 degrees is equal to 0.08 meters over t, and delta t is therefore equal to Yep, you have an answer? You could, but on the x-axis, there is no acceleration, right? So you're going to get vf squared is going to equal to...
the vertical deflection, so it's the vertical form.
Correct. But you don't know its final velocity, though.
It's zero, no? You want to know?
No, not necessarily. The vertical deflection would be what is its y position at the end compared to the beginning. So its final velocity is not necessarily zero. Do I have an answer? You guys have an answer for time? Anyone? One times 10 to the minus 6? Yeah, that makes more sense. All right, we have time. Got that? Okay. Okay, so I have my delta t. The next part is pretty much just kinematics. I mean, it's been all kinematics up until now. We just need to solve for our delta dy. Do you guys remember what the formula was for delta dy when there's an acceleration? It's the one with that's the harder of the three or four one, yeah? Well, that one doesn't use time. We need something that has a variable with time. We could use that, sure, but are we looking for a final velocity or are we looking for final position? Or the change in position? Position. So let's not use one that has velocity in it. It's going to be, do you guys remember this? Delta dy is equal to v initial times time plus 1/2 at squared. You guys remember that? Yeah. Hmm? Ah, yeah. So in this case, VI, is it just the VI of the initial problem, or do we need to break it down into another component? Is it just regular VI, or is it VIY? Yeah, it's VIY. Which means that, come on. Which means that we're going to have V, or actually I'm just going to write down numbers now. 80,000 sine 4 degrees times delta t, which is 1 times 10 to the negative 6 seconds, plus 1/2 times the acceleration, which is 2.87 times 10 to the 11 meters per second squared, multiplied by time squared. 1 times 10 to the negative 6 seconds squared. Do you have an answer? Question? Which one? You're right, except, look, if you want to use this formula, you have to find acceleration and time. So you have to calculate it, and you have to calculate time, right? So at this point, why use an extra step when you can just go directly straight to the answer? You could, you'll get the right answer if you want.
But we need acceleration and time here.
Exactly. But if you do it here, all you're solving for is final velocity. If you do it here, what you're solving for is the answer that you need. Is the whole point there? C'est pour ça que j'ai dit au début que ça n'allait pas marcher. Ouais, ça dépend. Yeah, Felix? Oh, yes, the acceleration should be negative. Felix has a great point. Acceleration should absolutely be negative. You know that because it's going downwards. Simple as that. It shouldn't change much. Hopefully it doesn't change your final answer. The acceleration. Makes sense. Because over there I was solving for over here, I was solving for VIX. And here it's VIY. normal. Do you guys have an answer? Yeah. This is, remember at the beginning I said the answer is not going to work out? I'll explain why in a second. And actually it never passed the 8 centimeters. So it went up and down and hit the bottom part before it did 8 centimeters. That's why my problem ended up not working. Can I have an answer? It should give you a negative number. Mine is 0.42. Oh, 14. Okay, this doesn't make any sense whatsoever. That's because the problem isn't taking into account how long the parallel plates are. So what's actually happening here is the object is being launched like this, and it's actually doing this and hitting somewhere here. And what you guys calculated is if there was no ground here, this would go down, and this distance here would be negative 0.14 meters. Okay, that's what you guys found. No, that's your answer. Yes. Theoretically, you're right, it does. But it's so minimal because the you can see how big the acceleration is. The number that you have for acceleration, could you turn the page? The acceleration is going to be that big for the electrostatic force, and plus 9.8 for the gravitational force. So this number plus 9.8 is basically just this number again. All right. Those are the two problems I wanted to practice, guys. Those are the two problems I wanted to practice so that I feel like you guys are okay after last class. This is the exact type of question I'm going to ask you next week on the quiz. There's going to be 2 questions, one on each of these topics. Okay? So next class you guys come in, it's Tuesday. You'll be doing the quiz for the first 30 minutes, 2 questions, then you have a lab to do for the next 2 hours. Okay? Solve this before then. I'm happy to help you guys however you need be. There is a lot of practice problems on Moodle. Try them out. There are answers. They're not my answers. So hopefully they're right, but there are answers there regardless. Okay? Take a 5-minute break. Come back here. 49. Yeah. I'm asking you guys, on the screen here, what do you see? What does it look like to you? It looks like a topographical, like, you guys know what I'm talking about? But there is actually a field of physics called geophysics, where what they do is they map the electric field of one aspect of geophysics. They map the electric field of an entire area. Now this might look like, oh, look at all the complicated electric field and the potential lines, or that we'll go there in a second. This must be like some really complicated place, but actually, if you think about it, how many objects in this room produce an electric field? Anything that has a charge produces an electric field. So you guys, each of you have at least 3 objects that are producing an electric field. Calculator, cell phone, laptop, right? We all have that. We're all producing an electric field. If you're next to a power plug, that produces an electric field. If you're under a light, produces an electric field. If you're underneath wires, there's wires all around in the ceiling, the columns, the grounds. There is huge power lines that flow through the city. by electric fields, huge amounts of electric fields. We deem them to be safe. I mean, I have no idea. No one really has an idea how safe or unsafe they are. But we have a pretty good guess that, okay, sure, it's not going to cause cancer. Point is, it does make other things behave differently, right? So if you have really long power lines, right, those produce a big electric field, and therefore you can't have really powerful, really like sensitive things next to big power lines. Yeah.
So we're telling we're smart about electric fields and we don't have a clue
We do have a clue, just we don't, we never actually know for sure. Can you say with absolute 100% certainty that every single time I drop my pen, it's going to fall down? Okay, well, what's going to happen if I do that? It's going to fall. Can you guess what's going to happen then? It's going to fall. If I do this a million times, how do you know the million and first time isn't going to be that time where it doesn't fall? You just can't know, right? That we have a pretty good idea about the electric fields. We don't think that they're cancerous or whatever, but maybe there is a limit to how big an electric field could be before it starts disrupting the way your electrons actually move. Imagine being next to like an electric storm. I don't imagine that being very helpful. All right, so today's talk is going to be about that. It's going to be about electric potential lines, and that's going to be complicated because now we have electrostatic force, we have electrostatic, electric field. We're going to add two more to those, and they're both electric something, and the formulas look basically exactly the same. Before that, I want to just do a very quick review on this because you're going to need to know it for today. First things first, when you have a positive charge, the electric field lines are flowing outwards. Please remember that. And if you have a negative charge, the electric field is flowing inwards. Okay. You need to know that electric field is a vector. We remember that. That's no problem. We need to remember that the field lines go in the direction of what would happen if you were to put a positive test charge. A test charge is very important. It's a theoretical charge, which has, we're calling it positive, but when we're calculating things with a test charge, we don't even assume that it's there, right? So kind of like the electric field. So if I were to put a positive charge next to a positive test charge over here, if I were to do that, then it would feel a force going in that direction, and that's how I know that's where my electric field is going, okay? And that electric field is the force per unit charge, okay? So just try to remember those things, all right? The electric field is the force per unit charge. If you remember, it's F divided by Q. You guys remember all those things? Yay. Move back a little bit more and talk about your mechanics course last year when we're talking about potential energy, all right? And if you have an object at a certain height and at a certain mass, it's going to have a certain potential energy, right? How could I increase this object's potential energy if we're talking about only the example on the left? What could I do to that object to increase its potential energy? Yes. Increase the, what do you mean the edge? Oh, the H, yes, the H. Yeah, you can increase the height, okay? What else can you do? Yep. Increase the mass, okay? So the potential energy here is dependent on m, g, and h. G, in this case, let's call it constant because we're always going to be dealing with Earth. And it's the same thing for the electrostatic potential energy. All right, and that's the topic of today. We're talking about potential energy and electrical potential. Confusing because they both have the term potential in it, but that's the same case. Ignore these examples here. I'll draw up another more simple one. If I had an object that was very positively charged, and I put a negative charge there, what's going to happen to that electric charge, that electron? It's going to what? It's going to be attracted and it's going to go downwards, right? Very similar to if I had an object and I put it here and I let it go a bit, it's going to fall downwards. If I put an electron, it's going to air bunny downward. It's going to fall downwards. And how could I make this? So this has some energy, some potential energy. How can I increase its potential energy? Think of this. Yeah. I can increase the charge, absolutely, or I could exactly increase the distance. So it's again dependent on the distance and the charge. Yeah. It would give it more potential energy. It would give it more. Let's go to the next slide real quick. If I were to show you this on the left, these two are the same height, but one's got more energy to potentially give to other things than the one on the left. So if you remember, if we're talking about the acceleration, which now we're talking about force, then it has to do with Q1 and Q2. So the higher the two charges are, the higher the force is going to be, therefore the higher the acceleration. Yeah? So far, so good? So let's draw these parallel. Know that the force of gravity is equal to mg. We know electrostatic force is equal to kq1 q2 over r squared. What we need to remember from last year, and this is a very universal law of energy, is that work is equal to force times distance. You guys remember that? And you can use this to find the work of anything. If you want to find the work of friction, use the force of friction. If you want to find the work of gravity, you use the force of gravity. If you want to find the work of anything, really, you use that force. As long as it's uniformly applied. That's why you can't use spring force in this. It applies the same way here. So we said that the gravitational potential energy, I'm going to change it to PP actually. Which letter did you guys use for potential energy? Was that? EP? Okay, that's going to be confusing because of electric field. Let's do PE. Do you guys mind? No? Okay. PE. Yeah, potential energy. Potential energy is the force of gravity times the distance, right? So m times g times h. So similarly here, electrical potential energy, I'm also going to call it PE because it's just potential energy anyway. It's going to be kq1 q2 over r squared times some distance x. Could you guys really quickly give me the expression for the force on Q2? All right, so I drew a little diagram here. All right, how do I know how much force to calculate based on this? What's the formula again? And it's right there. Just read it to me. Exactly. It's kq1 q2 over r squared. All right. And so how much potential energy it has? Well, we need to know two things about the potential energy. We need to know its charge, and we need to know its distance, which is r. Okay, so I had to multiply by the distance. So this x, well, that's just r. And therefore that r and one of these r's, they cancel each other out. So what I end up with is the electrical potential energy is equal to kq1 q2 over r. this expression is good, but it's not perfect, okay? This object, I'm assuming it's a very big object that we use in a different lot of places, kind of like Earth. Every time we do a calculation, we always have to take into consider Earth. Every time we take into a calculation, we always have to take into consideration Q1. So why don't we find an expression for potential energy per charge? That way we can just be like, this is too specific. This expression only works if there is a Q2 there. Let's find an expression that works regardless of what the charge is here. Let's find the potential energy per charge. Okay? So if I want to find the potential energy per charge, right, I would take this expression divided by Q. I can get rid of that Q and make it so that my expression depends only on the actual object that we're talking about. So if I'm talking about this object, I can figure out what the energy per charge is anywhere around it. Okay? And that is actually what a volt is. And we're going to call that electrical potential. So don't get confused. We have potential energy and V as electrical potential. And that's measured in volts. Energy is measured in what? Joules. So if it's joules divided by coulombs, or joules per coulomb, that makes sense because we said per charge. That's going to be equal to voltage. Yeah. So that's the beauty about this, is that let's say this is producing an electric field, right? And therefore it has a voltage. If it has a voltage, you don't need to know what I put here in order to figure out what its voltage is. Its voltage is its voltage, right? You would only know the energy if you knew what was here. And that means you need more information. And having that extra information isn't always convenient. So having all the information available for this that's applicable to all charges is more useful in a practical life. So we came up with this unit of volts. Yeah. Not that it's positive, it could be negative as well. Yeah. Yeah, the bigger charge could be positive or negative. It will have a potential. It will have potentials at every distance. So this still depends on R, and it's inversely proportional. So that means that if I were to take a measurement of the voltage of this object close to it, it would be higher than if I were to take the voltage all the way over here, right? And that makes sense because an object has less potential energy. Yeah. 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 Very good question. You got it? Well, I'll explain it just in case it's not super clear. This is for positive test charge. So if I were to create a very positive object near a positive test charge, then the closer you get, the higher the potential energy. Right? It's the opposite is going to be true. We're going to do some problems that hopefully will clear that up. So again, here I have my two boulders. We all agreed that the bigger boulder is going to have a higher potential energy, right? And out of our two charges here that are located there, they have to fall, quote unquote, fall towards the negative plate, right? And they're at the same distance. So which one's going to have more potential energy? Which one? Not the heavier one, but the more charged one. I guess it could be heavier too, but it's not by its mass that is determined, it's by its charge. So we're going to say that the 2Q is going to have a higher potential energy. Now, which one has a higher potential? Or can I even say that? Exactly. The potential depends only on that bigger charge. Therefore, what I really care about is the voltage difference between those two plates, which I'm going to call delta V. And delta V is delta V regardless of which charges I put there. Are you okay with that? So now it's a little bit about nomenclature that's important to understand. There is a positive end and a negative end. And for convention's sake, we call this high potential. And we call this side low potential. And if I put a proton near the positive end, so I'm putting a positive charge near the positive charge, it's going to have a high potential energy because it's got more room to move towards the negative charge. So that's got high potential energy, whereas this one's, when it's over here, it's going to have low potential energy. Okay? Yeah. No? Question? Yeah. The potential or the potential energy? The potential energy, because think of it, if you were to hold this on its side so that the negative is at the bottom and the positive is at the top, now you can draw the parallel with the mass falling on the planet, right? So when it's high up, it's got a high potential energy, and as it gets closer to where it's the low energy state, it's going to have the low potential energy. Okay, that makes sense? If I had an yeah, go ahead, Maxine. It's the voltage of B minus the voltage of A. So VB minus VA. If I had an electron, what would change here if I had an electron? Instead of a proton at point A, or it doesn't matter even if it was at point A, but let's say I scratch this off, blah, 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 gone, and here I drew a negative charge and a negative charge here. What changes and what stays the same? All right. Yes, here is high potential energy. Gabrielle, do you want to ask me of that? Yep. So this is going to be low potential or low potential energy? Yeah. Low potential energy. And do I switch my high potential and low potential? No, I don't, because it's irrespective of the charge that I'm putting in there. Okay? So this is still high potential on the left, and it's still low potential on the right. Yeah. Because now the electron is going to try to fall that way. So it's got more energy to give to become there. No, I'm saying this is before and that's after. It's this object falling that way. Yeah. I have another question for this, and now I'm drawing a blank. Oh. Okay. That in gravity, that potential energy, when it's up here, becomes what as it falls? Kinetic energy. Same thing here. That potential energy, so this electron, for example, as it starts getting closer and closer, obviously it gains more and more velocity. And as it gets more velocity because of the electric field, it's getting more and more kinetic energy. We all good with that? Yeah. No. So so high potential. So I'm going to just erase this thing here. High potential, that doesn't change. Low potential, that doesn't change, okay? So for a proton, it's got to be high potential here. For an electron, it's high potential on this side. It's back. Okay? Yeah. Are they attached together? What do you mean if I had a proton and an electron? Oh no, that's the same electron that moves in that direction. Yeah. Okay. Yeah. What do you mean? Or which point? So if you were to take the proton here and the electron here, they would have the exact same potential energy. Yeah. Exactly. And overall, the energy is conserved. So that potential energy all becomes kinetic energy. That's a good question. Okay? Here's a summary, and also something that I have a really hard time remembering. So there's a slide on it about it. Is what is positive work and what is negative work? Well, if you're getting tired doing it, it's positive work. If you're getting less tired doing it, then it's negative work. If you're climbing upstairs to come to the 5th floor, are you doing positive work or negative work? Positive work. If you're a proton moving towards a positive plate, are you doing positive work or negative work? You're doing positive work. Okay? No work. If you're holding an object and moving, theoretically you're not doing any work. Practically speaking, yes you are, but theoretically no. Yeah, sure. It's really crummy because I got the extra room for you guys, and now we're here today when we don't have the extra room, and on Tuesday there's a lab, which that means you're going to be here. I'm sorry, that's just the way it works, right? I'll try to get them to flip at some point. These chairs are the way. I have a one with a back seat. I'll sell it to the highest bidder. Okay, but you guys, the first come, first serve from now on. I never sit down, so whoever takes it is theirs. Okay. Take it. So the whole point of this is to learn about voltage. Okay, voltage is very, very, very important when it comes to electricity. I'm sure you've seen like, do not touch these 12,000 volt wires, or you have like a 12-volt battery in your whatever. What's that? You're not supposed to touch those. That's what we're working towards. All right. First things first, let's draw what we call equipotential lines. What that equi and equipotential, what would that equi mean? Equal, all right? So lines that pass through potential areas that have the same potential. I'm going to ask you guys a question here. We said that potential is equal to KQ over R. Okay? And if I picked any point on this left diagram and I drew a dot there, and I said that that was at a distance R, that point there, actually like before I even go there, this Q here, what does that refer to? Is that the Q of this charge in the middle or the Q of this test charge? Yes? Charge in the middle. Okay, perfect. So that's not changing. Q is not changing because I'm looking at the same charge for all of my further questions. All right, so at that dot that I just drew there, at a distance r from the center of that positive charge, the potential is, let's call it V. Okay? And what about if I drew a dot here, another dot along one of those lines at a distance r, right? What would the potential be there? The same v, right? And this v here that I drew first and the second v that I drew have the same value because they're both at a distance r. Okay, nothing's changed. It's just located somewhere else. And if that were the case, that means there's an infinite number of dots around this at a distance r that have the same exact potential. And we call that, if we have a line that passes through all these, we call that an equipotential line. So far, so good? Is there another equipotential line around that test charge, around that positive charge, that point charge? Yeah. There is infinite number of equipotential lines around this. Right? Each of those points along those lines will have the same voltage. You guys know what a voltmeter is? Some of you might have used it before. You'll definitely be using it in this course. In fact, our next lab uses it. This is a voltmeter, right? Actually, there's also an ohmmeter and a nanometer and all that stuff, but it's overall is a voltmeter. And it's got two ends. And what these two ends do is when you touch them on two different things, it'll tell you the voltage difference between those two things. So this is, if my left finger is 20 volts, and my right finger is 80 volts, and when I put my fingers on it, what is it going to read? 20 and 60 volts. All right. 60 volts. It's going to read the difference between them. Now, if I placed my voltmeter, on this outer line, what should it read? Zero, absolutely, because they're both at the same potential. Therefore, their difference is zero. If I were to place, and this is a positive charge, so let's see how much you guys know this. If I put this on the inner line and this on the outer line, what value should I get? Don't give me a number, just tell me if it's going to be positive or negative. What if I did this? There is no way to know. It depends on the machine. All right, that was a trick question. How about this question? If I put this one on the plus side and here, and I read 10 volts, okay? What am I going to get when I read here? Smaller or bigger? Smaller. Okay, very good. Smaller because the radius is getting bigger, the distance from the center is getting bigger, therefore the denominator is getting bigger, voltage is going to go down. So this is actually a bigger number. Then smaller number, and even the smallest number here. Okay? You guys understand? Please, 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 please remember that, because that's the major part of your lab that you're going to need to do. All right. On the right, I have two opposite charges, point charges again. We're going to get more complicated later. I have two oppositely charged point charges. We're doing good on time. Okay. And in the middle, what would you say the distance is between the left and the right? If it's the same, then they're equal, exactly. So I can call them both R. All right. And how do I find the electric potential at that point? Well, I got to do that. The total charge, the total voltage. The total voltage is equal to the voltage from the plus charge plus the voltage from the minus charge, which is equal to positive KQ over R minus KQ over R, which gives me what? What? Yeah, exactly, 0. So if I'm at any point between two oppositely charged particles, but they have the same magnitude, at any point, if their distance is the same, my voltage is going to be, yeah, 0. So that means here, if I drew a dot there, and this distance is equal to this distance, or a point here, where this distance is equal to that distance, then that means all of these points are 0. And I can draw a line where all the voltages are the same, because I need to draw equipotential lines. So there's going to be a line straight down the middle that's an equipotential line. Let me ask you another question. Yeah, that's the mid, those are the midpoints, all right? But the equipotential lines only aren't on midpoints, it's just wherever the voltage is the same. So if this distance from here to here is R, right? And therefore its distance from here to, whoops, from here to here, let's call that R prime, all right? All right, so this distance, I'm going to call it R. This distance, I'm going to call it R prime, and you're going to feel a voltage there. There is another point just below the axis of symmetry that's going to have the same distance here and here. So right at this point here, I'm going to have the same voltage as that. So there's going to be, these two are equipotential. But in the middle, I can't say that. I can't say that, I can't draw a line here, because that would mean that here, it's going to have the same potential. And that's not true necessarily. And the way to do it, and I mean, you can do it by trial and error, which is what you guys are going to be doing on the lab. But what you'll find out is that equipotential lines, right, cross electric field lines at a 90-degree angle. All right, so you see here, the ones that I drew, this one that I drew, this equipotential line crosses all of these at a 90-degree angle. That one was easy. Look at this one here. This equipotential line crosses the electric field line 90 degrees, 90 degrees, 90 degrees, 90 degrees, 90 degrees, 90 degrees. All right, and that's how you would draw those electric field lines, right? So if I were to draw something at 90 degrees here and at 90 degrees here, it would look like that, all right? If you notice, I'm trying to draw them at 90 degrees, and then I have to make it so that it's 90 degrees there, and 90 degrees there, and 90 degrees there. So it looked kind of like that, without the blip. And the same thing on this side. Something like that. Any questions? Okay. So here is now all that explained, right? So the electric field lines and equipotential lines for two opposite charges. This is what the diagram is showing. You have to make them those lines perpendicular to each other, all right? Take that for granted unless you want to do some pretty complicated linear algebra, and I know how much you guys are enjoying that right now. My course is better, right? Just say yes. Thank you. The work that we can do could be done backwards. So what we just did here in this example is we had the electric field lines and we worked our way to equipotential lines, but it's true the other way around too. If I had equipotential lines, I can work forward to get the electric field lines. So assuming that at the center of this, there is a charge and a charge there, right? I can draw an electric field line going outwards to the right, for example, and that will perpendicularly cross every single electropotential line, equipotential line. So it's crossing them at a 90-degree angle. You guys see that? Now remember, in that first slide today, I told you guys to remember one thing about electric field, and that was what? In the first slide today, after we did those two problems, I said, here's a review. Please remember this for the end of this class. The electric field is a vector, so I can't just draw a line. Equipotential lines are not vectors, so I can just draw a line. But electric field line is a vector, so I have to give it a line, a direction. Why did I choose that direction? How did you know it was a negative charge? You're right, it is a negative charge there, but how did you know? It has negative volts, right? And the volts are actually, now please pay very close attention to this. As I'm going away, is the voltage increasing or decreasing? It's increasing, all right? Because it's becoming less and less negative. Are you okay with that? Okay, so we drew one. That's no point in just drawing one. Let's draw a whole bunch. So you guys do this on your page. Try to make electric field lines such that they intersect everything at a 90-degree angle. It's not going to be easy, and it's not as it should look something like that. Sure, it should kind of look like the drawing here on the right, essentially. And right at the center of this, is there going to be an electric potential? Danielle, what do you think? Yeah, they're all going inwards because they're both negative charges. Back to my question here, though. At that exact point right in the middle, is there an electric potential? How do you know? Because what? Well, I didn't draw every arrow. There's an infinity number of arrows. First of all, I'm not asking about electric field. I'm asking about electric potential. That's different. So there's no arrows at all, in fact. I'm talking about potential. Is there an electric potential there? If yes, how do I calculate it? If no, why not? What do you think? Well, potential has nothing to do with movement. Potential is potential. Yeah, what do you think, Sammy? If we're talking about force and electric field, you would be right. But we're talking about potential. How do I calculate potential at a certain point? Yeah? It's not the difference, it's the sum. All right, so let's look it up. If I had to check at the middle there what the voltage was, then it would be, well, it would be KQ over R. And it's just, let's assume that it's a negative charge, so it's negative, plus another distance, another voltage, negative KQ over R, which is equal to negative 2 KQ over R. That's not zero. Yeah. Pardon? Oh, it's a raison. C'est a moment, it's my mistake. So the potential at the middle is not zero, all right, because it is not a vector. If it were a vector, then yes, you're right, they would cancel each other out because they're going in opposite directions, but it's not a vector. You just add them up. What's the electric field at the center? Zero. That's a vector, so they do cancel each other out. If I were doing vectors, right, so the vector, the electric field from this charge would be to the left, the electric field for that charge would be towards the right, and then they would cancel each other out. That's true for electric fields, but not true for electric potential. Okay? So far, so good? All right. Yes. No. Different things. Over here, I have a point charge. And I'm trying to find the equipotential area of this point charge. In my last example, we drew it as a circle, but in fact, we're in three-dimensional space. So a point charge is going to have an equipotential sphere around it, a hollow sphere around it. All right. So everywhere along this hollow sphere, anywhere along here and along back there. So a point here where I just drew a circle, right? That point there and this point here, they should have the same potential. So the delta V for those 2 points would be 0. Okay? What could you say about the voltage on A, B, and C? A, B, and C. They're all the same. So the potential difference is 0, exactly. This picture, what does it look like to you? Half sphere with a positive charge in the middle. Imagine it was a full sphere with a positive charge in the middle. What does it look like? What if I had, so there's a positive charge in the middle. What if I had a negative charge out there, and that negative charge is doing this constantly? An atom, exactly. So this is kind of like the electron cloud of an atom. And we have to determine, well, if we had an electron out there, in the outer shell, and an electron, oh, come on, and an electron down there in the inner shell, which one of these would have lower potential energy? The one closer would have lower potential energy. So this is low PE, and this is going to be high PE, all right? And so when you excite an electron, when you give an electron more energy, it's going to jump up, right? If you give the electron more energy, it's going to jump up. If you want to relax the electron, right, the electron will jump down to a more stable electron cloud, all right? However, because this cloud is smaller, this inner cloud is smaller, there is less space for electrons to be there, right? So there is, if I put another electron there, now these two electrons are going to repel each other and there's going to be no more room. This one's going to require a huge amount of potential energy to be able to shoot downwards, all right? In fact, it's more stable where it is than it is to be shot downwards. This first orbital, do you guys remember how many electrons fit on it? 2, all right? And the reason for that is because the shell is smaller, there is more electrostatic forces between the electrons, and it requires a lot more potential energy to bring that electron down. If there's only one electron in that shell, right, and I remove this one, let's say, let me just erase it. If I were to remove that electron so that there's now only one electron, this could easily jump down. It requires less energy to be here than it does to be there. So automatically, you're going to end up with a configuration where your atom has the inner layer full before the outer layer becomes full. So guys, does that make sense for you guys? Deep down, chemistry is just physics. Yeah. To be able to come down into the next shell. If the smaller shell is full, you need a lot of potential energy, or you need to forget about potential energy. You need a lot of energy to be able to come down, because that shell is already full and there's a lot of electrostatic repulsion. Okay? So far, so good? Last class we did parallel plates. So I'm going to talk about parallel plates. Which one of these plates, this one here, all the way on the right, or this one here, all the way on the left, has a higher potential? Why? There, so we, so if we were to go back these slides, all the way back, it's high potential when it's positive, low potential when it's negative. So which one is more potential, left or right? Positive or negative? Positive, A, exactly. So there's going to be high potential. There's going to be low potential. What about this here compared to this? Which one of these are going to be higher? This one's going to be higher than this one. So if you were to say that V2 is greater than V1, if this is V2 and this is V1. All right, I see like I'm losing you guys a little bit. Take a 5-minute break, come back, you can outside. Oh, we're starting here. Any questions about this? Okay, moving on. Take a gander at this question. Tell me what you think. I have a point. I have a proton that I've placed at point Q. Is it going to go to the left? Is it going to go to the right? Is it going to change speed or not? Yusuf, what do you think? A proton is, say that again? Well, yeah, if it's just a proton, like an atom, I can't take a proton out of a nucleus or something. But if I have just a proton, yes, I can. You think to the left? So I mean, he said to the left. You guys agree with that? I agree with that. Is it changing speed? Increases speed. Why? Exactly. It's getting closer and closer. There's a force. If there's a force, there's an acceleration. So the answer is C. Forget about what the question asked you here because it's awkwardly worded. Tell me what you can tell me about the potential at 1 and then the potential at 2. They're equal. So V1 is equal to V2. What could you say about V1 and V3 and V2 and V3? V3 is bigger? Smaller? Smaller? V3 is smaller than what? V1 or V2? V3 is bigger? Why? If it's further and you're dividing it by a bigger number, because remember that voltage is equal to KQ over R. So it's V3 is lower. Yeah. Yes. Guys. Potential energy, we have no idea because we don't know what kind of charge you put there. Yeah. Exactly, because remember that's that second Q in the formula. Yeah. All right. Here's a more mathematical question. So I have a charge, a proton, traveling at 800,000 meters per second towards something that's going to make it stop. Okay? That kinetic energy is going to come and become what? Potential, exactly. Is it traveling towards a positive charge or a negative charge? Positive or negative? All right, here are different answers, so there is a disagreement. Positive because what? Exactly. All right, positive because it's going to start getting repelled and it's going to slow down. If it was negative, it would speed up and it would actually go faster into it. It would never stop. Okay? Did you guys ever hear that your atoms are actually never touching? You're made up of separate atoms, and those atoms cannot physically touch because there is so much electrostatic repulsion between them. And as you get closer, as you jam those atoms closer together, that means your R is decreasing, their nuclei are the same charge, therefore those atoms actually never, ever, ever touch. You're made of a web of atoms, not a string of atoms. Let's talk about where that kinetic energy goes to. You guys said it goes into potential energy. Are you guys doing the whole, haha, I'm not touching you thing yet? Because your atoms can't touch? I showed that to my grade 7 students last year. They hit each other pretty freaking hard. If I had this proton that was traveling at whatever speed, and it's slowing down to a stop, is it going towards an area of high potential or low potential? Not energy, potential. High potential. Because it's going towards a positive charge where there's high potential. Okay? Is this potential energy increasing or decreasing? Increasing. Okay, so now we know that all that kinetic energy gets converted into potential energy, right? And the question is asking you, what is the potential of that point where it stops? Well, that's pretty easy, right? It's the potential energy divided by Q, because that's the definition of potential, is the amount of energy per charge. So find that potential energy, divided by the charge, get the potential. Do it. l'inverse. L'énergie cinétique transforme en énergie potentielle. Parce que ça commence à être en mouvement. Sans qu'il y ait une force, on parle pas de force. So kinetic energy is slowing down because the object is coming to a stop. So it's losing kinetic energy, and by losing kinetic energy, it's gaining potential energy. So all that kinetic energy gets converted to potential energy. Yep. Yep. All right, guys, what did you get? What are the units? Which one? I think you made a mistake.
Story of my life.
It's 3,340 volts. Let me see what you did here. You forgot to square the velocity. You probably made a unit mistake, but there was no unit converted.
Oh, exactly.
Maybe it's I'm sent to the negative 27 the mass of oh no, you have it here. No. Yeah. Try punching it again. Or that's what it is, right?
Yeah.
800,000.
800,000.
Okay. Last question, then I got you guys doing something for me, okay? So here I have an object that goes from point A to point B. It passes through point A, it comes out through point B. What's the voltage difference between point A and B? So there's a delta V of 40 volts, okay? First of all, this is the proton, and the proton is going from positive potential to negative potential, or the other way around? It's going from positive to negative, and it's a proton. Is it going to be speeding up or slowing down? So that change in potential energy from here to here is a gain of kinetic energy, right? If I have a gain of kinetic energy, well, I mean, irrespective of what my initial velocity was, I can find the new velocity, right? Because I just have to find the change in velocity added to my initial velocity, and I have my final velocity, okay? So if you know what to do, do it. Yeah, you can say that it's losing potential energy and gaining kinetic energy. So you can call it a negative number. As long as you know which direction you're going in, it doesn't really matter. Exactly, that's exactly what it is.
There would be
So
one
there's
half
a-
mv2 plus q times delta v equals same thing on the other side. Second one.
You're overcomplicating it. It's all that potential energy that you gained or lost from between A and B. You don't care what happened before and after A and B. Just
Okay,
care
so
about A
it's
and
all
B.
the kinetic transform into all potential.
Or vice versa, depending on what the problem is. In this case, the potential is getting converted into kinetic energy. We know that because it's a proton heading to an area of lower potential. So it has to be gaining kinetic energy.
So it goes from but the
Exactly.
speed but at A to calculate the potential energy, is it the at A the kinetic energy would be equal to the potential energy?
I see what you're talking about. I would do it as a delta to make it more simple. So the change of potential energy between A and B is equal to the change of kinetic energy between A and B.
Increase
Of velocity.
velocity.
Yeah, I have to add that to the
I don't
initial
understand
velocity.
how like what the formula is.
We can do it your way too if you want. You can say that here you have 1/2 mvi squared plus potential energy, and all that gets converted to 1/2 mv final squared. You can do it that way.
But what
This
would be the
equals to this.
potential energy? Would the potential energy be this?
The
So
potential
the
energy would
charge
be this.
times 40?
Yeah, exactly. You got an answer? Well, no. So first, now you found the change in speed, right? Now you have to add that to the initial speed. Yeah. All right, guys. What did you get for velocity? Give me the change first. Yeah. How much? 80 something thousand, right? 50,800? I'm not sure that's correct. Let me see your work. Okay, so you might have made a mistake. Punch this in correctly? I think you're supposed to get 180,000. Oh, sorry, 130,000. So I think you're supposed to be adding about 80,000. So I'm just wondering if you were supposed to subtract this when you added it. No, you're supposed to add it. Punch it in again. Make sure you square your 50,000. It's supposed to be 83,000 something. How much? Yeah, that's right. Exactly, yeah. Yeah. Yes, what? Because what you found was the change in velocity. What is your answer?
8.75 times density.
Yeah, that's your change in velocity. Just add that to your initial velocity. No, you keep it. All right, so I should have gotten 87,500 and change meters per second. That's my change in velocity. And if I want to find my final velocity, well, just add 50,000 to that. So it gives you 137,000 some change meters per second squared final velocity, okay? at point B. You kind of did good. That's in English. All right, guys. Here's what I want you to do. Listen carefully. We're figuring it out again. It's a similar thing that you're going to be doing to your lab, right? So it's in the same vein as this, but it's not, I'm not asking you anything about potential here, okay? So last class, we all got hung up and started calculating potential for me. That's not what I'm asking for. For this, I'm asking for electric field, right? So there's 5 points on this chart. I want you to find the electric field at each of those 5 points, all right? And then I want you to sketch for me what the electric field map looks like. It's only electric field, no potential, okay? Everyone has to do it, but you can work with whoever you want, I don't care. But everyone has to do it, everyone write your name on it, and you have to hand it in at the end of class. Huh?
Yeah, Ash, did you see no? Did you see USB key, you know, the short one? Oh, this, something like this.
I think that might be yours.
That's mine, eh?
I guess so.
Okay, thank you, because I think I forgot it.